megawatts of storage deployed last year here in the United States. Energy storage is not just about the foundation for a more modern, clean, and reliable energy system, but is also a key sector for American geoeconomic leadership. However, as we will hear today, the international landscape is highly competitive, and the United States will need to do more to support battery innovation if it is to maintain an edge into the future. Finally, I'd like to remind everyone and take the opportunity to flag for those of you already not aware that later this afternoon, at the end of the day, around 5 p.m., we will be hosting another terrific public event with Patrick Pouyanné, Chairman and CEO of Total. Please do consider sticking around for that event. We'll have wine, as Mr. Pouyanné will be discussing strategy amid the low-carbon transition, and I'm sure energy storage will pop up in that discussion as well. And so, without further ado, let me welcome to the stage Akshat Rathi, for a short scene-setting presentation before our panel kicks off. Thank you very much.
Thanks for the introduction, David. I'm going to keep this presentation short. Presentations they tend to be boring. I'm going to make this exciting. There are very few words on it, mostly pictures. And I'm doing this in some way because of my editor. When I proposed to him that we should do a series on batteries, his first question was, aren't they kind of boring? And this is trying to prove that they are not boring. So 3 questions to answer today. Why should we care about energy storage? How do we get to the future that energy storage can make possible or has already made possible in some cases? And who are the companies or the people that can get us there? We've lived through one exponential technology curve in the silicon chip industry. We are living through another one in the battery industry. Exponential technologies are those that disrupt because we don't understand how to tackle them. People and companies don't understand how to make sure that they stay ahead of the curve rather than catching up. And so batteries are a technology story. They're also a geopolitics story. This is CATL, which is the world's largest lithium-ion battery company. 8 years ago, that was barren land. And now that's a $30 billion company making batteries for name a car brand in the world, and CATL will count them as their customer. It's also an environment story. David touched upon the fact that we'll need batteries for integrating renewable energy, but we'll also need batteries to clear up air pollution. That's Delhi. My wife grew up in Delhi, and she says she misses the fact that they used to sleep on the terrace, wake up to a blue sky and chirping birds, and now this is what they have to deal with pretty much every winter. And of course, batteries are not new. The first battery that was invented was 1799. If anything, batteries are the reason we have electricity. They were the first source of stable electricity in history. And so, every car that's there in the world, almost every car has a lead-acid battery that was invented in 1859. We've had batteries for a very long time, but there is a curve there of the lithium-ion batteries, which has made batteries such an interesting topic today. And that's because lithium-ion batteries are able to do something that previous batteries weren't able to do. They are energy dense, which means you can have lots of energy in a small space and put them in a smartphone. And they have a high power capacity, which is that you can withdraw lots of energy in very short time. That means you can put them in electric cars or eventually electric planes. And that curve, alongside that curve, is the other side, which is they are now becoming more ubiquitous because of the fact that their prices are falling. And this curve will continue to fall for quite some time to come. This is the only technical slide, and I want to bring in a little bit of the technology side because batteries are one side a very hyped industry because of all the potential that we talked about. But there is hype because it's poorly understood, and that's because most people don't know what's inside a battery. Our experts today will touch upon those, and I wanted to give you just a brief insight into what a battery is. A battery typically has these components. There are 2 electrodes, the cathode and the anode. there is, between the electrodes, you'll have a charged particle that will go back and forth. So when you're charging it, it'll go from one electrode to the other. When you're using it, it'll go from that electrode to back to the electrode where it was previously. And that happens through an electrolyte. And that is what a battery is. But the materials that make up cathode and anode have changed drastically, and that's what made lithium-ion batteries so interesting. We'll touch upon the fact that a lot of the batteries that we use today use critical minerals like cobalt, and what's the future of using batteries that have such a critical mineral in it. But I hope you keep this picture in mind when we're talking about batteries and what's happening inside them. Of course, if all that plays out well, the future is really bright. You might get electric planes. You'll have the mass market electric cars, which are sort of becoming a reality already in China. And you'll get maybe even 100% renewable energy. Perhaps not with just lithium-ion batteries, but other types of energy storage technologies. The companies that can get us there, these are the big players. Panasonic, CATL, LG Chem, BYD. Panasonic is Japanese, known here in America because of its partnership with Tesla. LG Chem is South Korean. But two of those are Chinese, CATL and BYD. China right now makes the most amount of batteries in the world, and will continue to do for decades to come, because the government has considered it to be a strategic technology to invest in. Of course, they're not the only companies. There's a lot of investments going in startups. America still leads the world, even though China has the capacity. America leads the world in battery innovation. One of America's, an American startup has now become the first unicorn, being $1 billion startup because of the amount of interest in this field. Before we go to the panel, I just wanted to say that much of this comes from guides that we are writing at Quartz. So in December, we published one on electric cars. In April was one on batteries. And I'm currently working on one about the future of the electric grid. I hope you can check that out. And I run a newsletter which is becoming a weekly at the end of this month. So I hope you'll sign up. And with that, I'd like to get our panelists and get our discussion about batteries into much more detail. You all have probably read their bios, but just briefly, so you have some context. We have Mitali Gupta from Wood Mackenzie, and Venkat Viswanathan, who's an assistant professor at Carnegie Mellon University. They've also been integral in my reporting on batteries, and they've helped me understand this landscape better. So I wanted to start with Venkat and get your thoughts on what do you think are the bottlenecks right now in battery innovation that are holding back some of the big useful applications that may be coming in the future?
Yeah, so battery innovation requires materials, and doing anything with materials is really hard. And if you look at the sort of trajectory of any materials innovation from conception in the lab to something that you would use, the rough ballpark time is 20 years. And most companies run out of money, and that leaves many, many great ideas either in the patent literature or even worse, in drawers of companies bankrupt. So I think that's the hardest part about battery innovation, which is chemistry, materials, and handling chemistry and materials is very hard. So I think that's one of the big challenges with respect to taking battery innovation and putting that into a product.
Yeah, and I want to say that I want this to be a conversation. And so whenever you feel like you have a question, raise your hand. I'll keep looking out for hands. Otherwise, don't feel shy. This is very much, batteries are one of those topics which seem big and important, but we want us to get into the nitty-gritties and really grapple with what the technology can do. Mitali, tell me a little bit more about some of the material constraints. So there's the innovation part,
Right.
but batteries are also, as we know, highly dependent on use of cobalt, on
Exactly.
lithium,
Exactly.
and what's the the current landscape of how these
Yeah.
critical minerals are playing out?
Absolutely. So when we say lithium-ion batteries, it's a whole family of different kinds of batteries that come under a lithium-ion battery. So there are different kinds of chemistries that exist within the lithium-ion family. The more common chemistry, which nowadays is being used for EVs and now more so for energy storage, is nickel, manganese, cobalt oxide batteries. So it's basically your nickel, manganese, cobalt with some lithium on the cathode side of things. And then you have your anode, which is made up of graphite in most cases. So because metals like cobalt are being used in these batteries, these metals are currently being derived from places like Congo, where we already have a lot of geopolitical issues going on. So there isn't enough supply which can kind of meet the growing demand that we are forecasting in the future, both for EVs as well as for energy storage industry. But not to say the industry is not looking to figure out ways how we can kind of go towards a low cobalt future. So the industry is now looking at batteries where we can actually reduce the cobalt content in cathodes and build high nickel cathodes. Most historically, the market that we had chemistries, NMC again, nickel, manganese, cobalt batteries with a 1-1-1 ratio, so equal parts of nickel, equal parts of manganese, equal parts of cobalt. But now the industry is moving towards 6-2, which is 6 parts of nickel to 2 parts of cobalt. There are also innovations happening around building 8-1-1, which is 8 parts of nickel to 1 part of cobalt. So vendors are really trying hard to bring down cobalt content in batteries, which is obviously going to help them safeguard from the risks of supply constraints that might occur because we just have limited supply. Right now, again, most of it is concentrated in Congo, but also is going to help bring down pricing. So to kind of touch upon what happened last couple of years, just as the market saw this huge demand of batteries for EVs and for energy storage, and the market started anticipating that we're going to need a lot more batteries, cobalt prices actually started ramping up pretty quickly last year. Early last year, we saw prices more than double pretty quickly, and there just wasn't enough availability in the market. As a result of that, a lot of innovations were sort of made by companies where they started rolling out chemistries where they were playing around with increasing nickel content and reducing cobalt content in batteries.
That, however, is not easy, right? You
Yeah.
and I have talked about cobalt a lot because cobalt is critical for how the chemistry works. And
Right.
so what does it take to reduce cobalt in a battery?
So I think in the spirit of how Akshat started to make batteries not boring, I'm going to try and describe this with an analogy with this whole nickel, manganese, cobalt game. Nickel is like the Lamborghini. That's what's giving you the energy. It's packing a punch and giving you all of the things you want. Manganese is sort of the cheap mass market Toyota that's adding sufficient sort of capacity on the road. The cobalt is really the cop car. Cobalt ensures that all of these people are going to be disciplined, that the nickel doesn't somehow move from one lane to another, and so on, right? So really the challenge is how do you keep this society in an ordered way without the cobalt, right? So that's really, cobalt's actually not the energy producing component in a nickel, manganese, cobalt oxide material. But it's really the one that brings order to that material, and that's what makes the material a cycle for a very long period of time. So people are thinking very, very hard about but not having cobalt as the cop car. There are many other options. The tricky thing is that most other possible options don't quite give the same level of performance as cobalt. I think that's the real hard thing, because you want everything that you already have and more, right? So you can't sacrifice anything, and so that's the hard part. So there's a lot of effort in DOE towards low cobalt. There was a very large program a couple of years ago from the EERE division supporting ultra low cobalt, ultra low and no cobalt. It's a hard problem, but I think many are working on it. There are some options out there. Chemex Power has come up with a family of materials broadly called ELNO, which is largely nickel oxide. I think there's promise, but there's still a long way to go before they're going to be prime time.
Yeah, and the other thing about batteries is that we can talk about the minerals are one part, but there are properties within the batteries that need to be tackled as well. So we talked about how they are energy dense, so they can pack in a lot more energy. The more nickel you have, for example, you'll have more energy. But when you start packing in more energy, they start becoming less safe. And there have been a number of fire incidents. You've probably come across stories of how a Tesla car, when it burns unlike an internal combustion engine car. That shouldn't be surprising. They're completely different materials. And so when you try and play and not mess up, but try and tweak the chemistry, you start to eat up in other parts of what a battery can do. It becomes a little less safe. And those sort of balancing the technology side and the safety side has been a crucial part of the industry. Can you tell me a little more about these fires? There have been fires not just in Tesla cars, but in energy storage applications in South Korea in the last year, which has sort of shaken up the industry a little bit.
Yeah. So from an energy storage perspective, South Korea was one of the biggest markets that saw a huge number of deployments last year. Because of the incentive program that was introduced by the government in South Korea, we saw a lot of projects sort of getting quickly deployed in the country. And just because of a lot of inexperience of developers and people really trying to package these systems and not citing them properly and not having a proper safety standard in place, a lot of these systems actually caught fire. So far we've heard there have actually been more than 21 fires across different facilities that were deployed last year. So that's a big number, and especially for the energy storage industry, because it's a fairly nascent industry and it's still ramping up. So that's definitely raised huge concerns in the market. And just a few weeks ago, there was a big fire in Arizona. So a facility which was owned by APS ended up catching fire. Again, investigations are still ongoing, whether it was a problem at battery cell level or whether there was a problem, with the inverter of the system, whether there was a problem with the fire suppression system that was in place. So investigations are still ongoing, but not to say, this definitely has brought a lot of concerns in the market, that we need to make sure that these systems that are being built to the best standards. We are ensuring that there is adequate safety, there are adequate fire suppression and detection systems functioning within these battery systems specifically.
And the other side of the equation is you've got energy and safety, but there's also a third one, which is power. So the difference being how quickly you can withdraw energy from a battery, and that's crucial for electric cars, not just so that you can drive a fast car, everyone would like that, but also that you can charge them very quickly. And I'm sure you've all come across these sorts of claims that people have made, that we'll make a battery equivalent to going into a gas station and filling up gas, 5-minute charge batteries. None of these are real at a commercial level today, and there are very good reasons for that. And Venkat has taught me a lot about why that's the case, and you should explain that.
Yeah. So basically, physics is in your way when you try to do anything fast, and the one thing that we know is you don't, at least in my world, you don't violate second law of thermodynamics, and so. The real challenge is when you want to try and do anything really fast, there are all sorts of heat generation issues that emerge, and the faster you try to do something, the more inefficient the system gets and the more heat you generate. So what you're doing is you're pumping an enormous amount of power, and the system gets more and more inefficient. So not only are you increasing the number itself, but you're also increasing the inefficiency. So you're doubly increasing the amount of heat generated. And so that's really sort of at the heart one of the major issues when you try and develop fast charging technologies. And an associated close issue with this is fast discharge, which actually will be important if you want to go to things like flying cars and so on. And so both have this sort of heat generation issue. And then the second one is really safety, especially when you charge fast. aggravate all the things that lead to fire. You have these sort of filament-like structures, much like snowflakes that form. They're called dendrites, much like the dendrites that come when you see snow melting. Those essentially, what happens is it penetrates through from the anode to the cathode, touches it, there's a short circuit, there's heat released, but really that's not what causes fire. The fire really comes from the fact that the cathode, the nickel, manganese, cobalt, or whatever, has oxygen. That releases oxygen, and that's the trigger. Once the oxygen comes out, then you have oxygen and possibly one of the best combustible substances, which is the electrolyte. And that's what causes this sort of catastrophic failure. Actually turns out, and don't try this at home, but it's extraordinarily easy to take a cell and get it to catch on fire. It's like the easiest thing to do, right? All you need to do is to tamper with the charging control and allow the voltage to go up above what is the specified limit. It's extraordinarily easy to get a cell to catch on fire. So what we have to do to keep it safe is extremely difficult, and it has taken some phenomenal engineering by EVs to keep the battery pack, which now has 8,000 of these cells, safe. And so it's an extraordinary engineering feat to keep all of these battery cells safe under the voltage window that should work. And so this is why be extraordinarily careful with the I guess now millions of products that use lithium ion, including those that you're going to keep in your ears with earpods, and I guess those that now you will have on your feet with like all these scooters and hoverboards and so on. So just have that thought when you put lithium ion anywhere close to your body.
This is the reason why on planes you're constantly reminded about how and where you should keep your lithium-ion batteries. I have a question in the audience there. Could you just introduce yourself and keep your question short? Thank you.
Henry Hetker, retired government. I wondered, what is the source of the oxygen that causes this fire? Is there a nickel oxide in the compound for the battery, or is it just the atmosphere?
No. So the cathode has, so the only way you the way to store energy is lithium has to like being in the cathode, and lithium is positive, so it likes things that are negative. And so you need the oxygen to, the lithium oxygen bond is what gives you the energy. And the reason you need nickel, manganese, and cobalt is if you just had lithium and oxygen, that's a very unstable compound. So the nickel, manganese, and cobalt is there to keep the material stable. So the energy producing component is really the lithium and the oxygen. And so the oxygen is there in the cathode.
And we have a question here.
Thank you, David Livingston. Again, two questions actually. Zooming out a little bit from the chemistry and helping to frame a little bit some of the the geography of this and why we're seeing the trends that we see. It struck me you have only East Asian players of the 5 largest players that you showed. What's interesting there though is that they're very different economies. Some have extremely high labor costs. Some have much lower labor costs. They're different in terms of their geography, to some degree different in their industrial model. Why is it, do you think, that there's been such a concentration of market power in East Asian battery manufacturers, number one? And then following on from that, what sort of policy mechanisms support battery deployment? Is it the same as we see for solar or wind, or do you need different sort of policy incentive mechanisms?
I'll give a little history and then I'll ask a question, which is, so the way lithium-ion batteries were developed, a lot of the innovation happened here in the US. So the different components that we talked about that make the lithium-ion battery work were developed here in the US. I don't know if people are aware, but the first lithium-based battery was developed by ExxonMobil. Well, Exxon when it was developed in the 70s, and this is during the oil crisis where oil companies were worried about oil running out altogether, and they wanted alternative energy, and they worked on these technologies. Of course, the oil glut came back, and then they dropped research in these spaces. The reason why Japan has been a leader is because Japan was the first country to pull all those innovations from different parts of the world and develop in Sony the first commercial lithium-ion battery. And so they got a head start in this space because of the commercialization aspect. South Korea, though, I am not sure. China, I can talk a little bit about, but do either of you know why South Korea became a leader?
Not anything in particular in terms of technology, and I just want to add one point that Japan and the UK were equally instrumental in the original development of the lithium-ion battery. I think one could be market. I think the fact that portable electronics revolution was largely being driven by companies in those countries, and of course, I think. The chemical industry also plays a big role. I think the fact that there's a very, very strong chemical industry in these countries would have also played into the whole ecosystem around making lithium-ion batteries, because it's just as much a chemicals play as it is a sort of product play.
And I mean, China itself has had its EV policy for a while now. They've introduced incentives in order to ensure that local manufacturing is getting more and more subsidies. Though I will point out one thing is the way Chinese EV policy started, they actually were supporting a different kind of battery chemistry back then, which is lithium iron phosphate. That's again another SEP chemistry within the lithium ion family of batteries. So China originally started with providing a lot of subsidies and incentives to local manufacturing and building a lot more on LFP batteries. LFP batteries are less energy dense than nickel, manganese, cobalt batteries. Most of the LFP batteries that were being manufactured in China back, again, like 3 or 4 years ago, were mostly being deployed for e-trucks, e-buses, and some for energy storage applications as well. But over years, Chinese government has kind of revised their policy, and as of last year, they ended up increasing the energy density under which the batteries would qualify for incentives. So as a result of that, now vendors are shifting towards looking at, again, nickel, manganese, cobalt batteries. The other thing that I also want to mention is last year was, again, an interesting year for energy storage space. So while there is this huge demand that is coming from the EV industry, energy storage industry is kind of riding on the cost curve of EVs at the moment. But last year what happened, because of the South Korean market where we saw huge deployments happening, and then LG and Samsung were primarily just supplying to the domestic market, global market actually felt a supply shortage for batteries for energy storage or grid applications. US was hit the hardest because vendors just couldn't get a hold of batteries from these Asian vendors last year. So what started happening was vendors here in the US started sourcing batteries from China, and so we actually saw a huge interest in LFP batteries for grid storage application last year. And this is one of the trends that we expect to continue even this year and next year, where we will see some divergence in energy storage space from EVs, where we'll see a lot more LFP or lithium iron phosphate application in energy storage industry.
Yeah, and these policies can have a huge impact on how corporations behave. So Panasonic and Tesla, for example, had a sort of monogamous relationship until earlier this year when Tesla moved to start a gigafactory in China. And because it would also want to be able to qualify for subsidies that all electric cars are getting, it needs to buy a Chinese domestic company made battery. And so now they are open to sourcing their batteries, not just from Panasonic, but from everybody. We have a question there.
Dick Morningstar, Chairman of the Global Energy Center. Following up on David's question on the different economies in Asia, as luck would have it, I was changing a lithium battery last night in my car key. And it turns out that this lithium battery is made in Indonesia. Is the same thing happening in Asia that has happened in industries in the US, where manufacturing gets shifted to different regions in the country or to Mexico or wherever? And so cheap labor in a place like Indonesia, do they end up being a primary manufacturer, or where the technology may be in other places?
So the battery you're probably talking about is either a non-rechargeable battery or is one of those single-use batteries. Is that right?
Or is it a button cell or?
Yeah. So those are batteries that are a tiny, tiny, tiny fraction of the market. So the brands we think about, Duracell or Everready or these button cells are they might get manufactured in India or in Indonesia or in South Africa, but those don't really count into the space that we are talking about right now, which is lithium-ion technologies. And having been to CATL, which is the largest battery factory, and a few others actually, the amount of automation in there is phenomenal. So that place had 15,000 employees, but that's a big number, but the number of employees within the factories were far and few. There were long corridors all the way to the horizon, and you had 5 people in those corridors. So automation has already come to this space, and it's not tied to the labor costs that David picked on.
I would just add one point to that. I think it will happen in segments, and I think you should ask the question why China was able to successfully start lithium iron phosphate. Right? There's so much lithium iron phosphate produced in China. And the reason is because it's easy to do. Right? The chemistry was not complicated. It was inherently safe, much safer to, it's very hard to pull out the oxygen out of the iron phosphate. So it was an inherently safer chemistry to handle. So you didn't need to get it right to make something that was 90% good, and 90% good was still very good. And the sort of safety challenges were not as big. So I would guess that many of these sort of easier chemistries will become ubiquitous. Everyone will be able to make it. And then I think we will see this where pretty much everyone should have their own supply of lithium-ion cells for their own market and other markets. So I think it will be very easy for lithium-ion plants to spin up now. I think that the technology is there. The know-how is now widely prevalent all over the world for many chemistries. I think this the sort of premium cutting edge, whether you have 80% of nickel or 60% of nickel, that's still sort of, there's still more science and art to that. But for the sort of commodity chemistries, and there are many commodity chemistries in the lithium-ion family that are maybe 80% as good as the sort of best. And I think those will become easy for everyone to make.
The other thing I would say, and I'll come to that question, is that economies of scale operate in these technologies that must be appreciated. So, and this is not just true of batteries, but also of solar photovoltaics. So China is also the leader in making solar cells. And the way it works is if you have a large, if you lay out a large factory, you're able to source your machinery at a lower cost. You're able to automate it more, and all those add up to the curve that we saw of how battery prices are falling down. And so having large factories is one way to do it, and that's another reason why China, having these incentives and also direct subsidies. So a lot of Chinese states have provided, either free land or no taxes on the land that they're giving. And those are incentives that are playing into having these large factories, and why China is the leader in this space.
Phyllis Yoshida, Sasakawa, USA, retired DOE. In the late 90s, we were writing analyses when we were running the Partnership for a New Generation of Vehicles about the economic and national security aspects of not having any lithium-ion manufacturing in the U.S. And I know we did things to try to encourage some of that, but when I look at your list and I listen to the discussion that just happened, it doesn't seem to be happening. So what are the prospects for us rebuilding a domestic industry?
Yeah, there's a little bit of a historical point between that, where, of course, the financial crisis brought with it this stimulus package, where some of the money was deployed to try and bring in lithium-ion manufacturing space here in U.S. Some of the money went to LG in creation of a factory, I think, in Michigan. And some of that money went to A123, which is a US company at the time, was developed by, the technology was based out of MIT. The story is that A123 went bankrupt and then got bought by a Chinese company, and so that technology moved to China. And so that's also happened, but I think that's a very good question. Lithium-ion is back into the space because of Panasonic and Tesla, but what is the future for lithium-ion manufacturing?
I think economically it will happen everywhere, actually, because the cost, if you look at now the overall cost per kilowatt hour of the battery pack, transporting the battery is actually a non-trivial fraction of the cost now, given the materials have been squeezed. I think it will be important for everyone to make their cells locally. And so I think that's one of the reasons why this integrated approach of Tesla making the gigafactory at the top floor with Panasonic making the cells, and then the modules coming down, and then them integrating that with the motor and the power electronics. I think it has to be that way, because if you have to, and as we've seen with challenges being able to ship cars made in California to elsewhere, I think the transportation cost will become non-trivial. So I think the factories have to now be integrated if it has to hit the below 30K, 25K target for cars. So I think there will be lithium-ion manufacturing everywhere. It has to happen.
I would say, though, that is dependent on having the demand for electric cars.
Yeah.
So if there are no incentives to create that demand here in the US, that may not become a reality at the scale that we expect it to. Europe is going through some of that challenge right now. You've got France and Germany coming up with this battery alliance, pouring in a billion euros to try and bring local manufacturing capacity. But of course, at the same time, you have a Chinese company in CATL creating a battery factory in Germany. So you're going to get this reverse a technology play where the Chinese bought some US technology and are now going into Europe with that technology. Yeah. Sorry, just.
Hi, Chris Troy from Power Africa. So for our program, we've been supporting energy development across Africa, and then solar is one of those that we support heavily. And then there's been a movement to look at solar plus storage, because just supporting solar, it ends up that the US was not very competitive with the solar panels. But then if you add in storage, then there were or are still some competitive sources for the storage. But it sounds like you guys are telling some interesting stories and some data showing that it may not be going in that direction. So which chemistry currently dominates for a stationary thing, so you don't need like density for like for a car, but for energy storage? So which chemistry dominates for that, and then which geographies are really dominating in their growth rates of development?
Yeah, sure. So in terms of chemistry, as I mentioned, nickel, manganese, cobalt batteries are pretty much dominating the market globally as well as in the US. But as I mentioned earlier, we are seeing this increased interest in LFP, lithium iron phosphate batteries, just because of the whole demand and supply situation. The market already saw a huge shortage of batteries last year, nickel, manganese, cobalt batteries. And so the LFP vendors, iron phosphate vendors, started tapping into these nickel, manganese, cobalt supply constrained markets. The other thing that also led to a huge interest in iron phosphate batteries was pricing. So last year, just because, again, South Korea, huge demand, EVs are a huge demand of, are taking up a huge demand of batteries. So we saw huge increases in nickel, manganese, cobalt pricing last year for energy storage, not for EVs, but just specifically for energy storage applications. Again, markets outside Asia. And that's again why lithium iron phosphate vendors started selling in at very competitive pricing. Traditionally, lithium iron phosphate batteries used to be expensive than nickel, manganese, cobalt, but last year they were actually fairly competitive to nickel, manganese, cobalt battery pricing. So as a result of that, we saw huge interest again in iron phosphate batteries. The third reason why there was a huge interest is fire safety. So as I mentioned, fire safety is becoming a priority for the energy storage applications more and more every day. It's really important to build these, systems safe to ensure that, you can site them in locations like New York City, where, we have some of the most stringent requirements around fire codes. So we need to ensure that these systems are safe to be deployed and populated and in urban centers. So that's another reason why there is, again, a huge interest in lithium iron phosphate batteries as well.
And a little bit on the geographies. I mean, I live in the UK, and there have been incentives for energy storage, but nowhere close to the sorts of incentives that come out of, say, Australia or South Korea. What are the geographies where energy storage applications, where you're trying to combine some of the renewables?
Yeah,
what are those? Which countries are leading there?
I mean, US is obviously one of the most mature markets in terms of energy storage applications. We've had mandates, regulatory support, incentives. Different states have announced, storage targets that they're trying to get to. Again, huge renewable penetration in the US, so we're seeing a lot more solar and storage getting deployed. So that's one of the biggest markets. South Korea emerged as a big market last year. Again, incentives that were provided by the government, more around, pairing your storage with solar or with wind. Australia again has seen huge deployments as a result of huge renewable penetration in that market as well. China, interestingly enough, has also started focusing a lot more on energy storage, specifically battery energy storage. Until a few years ago, they were more focused on pumped hydro and other storage technologies, but now they're looking very specifically at building more energy storage as well. So that's another interesting market that we're looking at. In Europe, UK and Germany, I would say, are the two markets that have showed a lot of energy storage applications. UK specifically doesn't have any incentives, but it's more market driven, so it's more applications that vendors are trying to target, like frequency regulation, ancillary services. In Germany, we've seen actually a lot more behind the meter storage, so more residential storage. So people are again citing their batteries along with their solar for resiliency needs, for backup power, to ensure that they're time shifting their solar.
Yeah, and these sort of batteries are also becoming, are getting used to do new things. So after Hurricane Maria in Puerto Rico, some of the islands are now are mini grids. So rather than being connected to the main island through these undersea cables, which get ruined in such catastrophes, they are now they have solar plus batteries on their own island, and they don't need to be connected to the main island. So that's starting to happen in places. In the UK and in the UAE, both places, I've written stories about something called a virtual power plant. So you take batteries in thousands of homes and you connect them together. You get permissions from each of those, of course, and then you use that, because they are all stores of energy, as a power plant, because that's the scale at which you can deploy them. And those applications are going to start to eat into natural gas power plants, because a lot of natural gas power plants in the US and generally around the world are used for peak demand. So when at 4 p.m. to 7 p.m. you have a huge increase in people using electrical devices or electricity in general, these power plants come on board, and solar plus storage and batteries are going to start eating into that and cut greenhouse gas emissions, but also this is becoming an economical approach for them. There are a few questions. One here, take one, and then after that.
Just a quick question on the point at which battery deployment, energy storage deployment might start to cannibalize its own business model. So if you think about a highly stylized model of the kind of the business proposition for batteries is it's an arbitrage between a high price and a low price over the course of a day or whatever the time period might be. The more of these that are deployed, the more you whittle away at that arbitrage opportunity, the more you smooth out prices over the day rather than having peaks and valleys. What are different players in the industry doing to anticipate that sort of trend, and what does that tell us as well about the way that we design policy going forward if we want to see continued growth for batteries?
That's a great question. I don't think industry has already reached that point that we are kind of already fearing from, that we'll have a lot more deployments and we won't be able to see any growth in the future. One of the things that's definitely happening in the industry is value stacking. So your batteries can not only just provide for one use case application or for just one revenue stream, but vendors are trying to build systems where they can actually use a particular battery system for several use case scenarios and can derive several value streams out of it. So you can use your battery system not only for your behind the meter battery system, not only for providing resiliency or backup power, but it can also be used to provide for grid services. So your utility can actually tap into your battery system during a peak event, and you can be a part of a demand response program, and you can actually get incentives from the utility as well, along with that battery providing power to you, as well as helping time shift your solar application. So a lot of those models are currently being developed. It's still a matter of time that the industry figures out a way that they can actually value stack different revenue streams. But as the industry matures, we'll definitely see the market moving towards that.
That's happening at the same time as the costs of batteries are going down. So right now you're not feeling the question you've raised is a very good one, and it's a valid one, but we are not feeling that play out as it would in a few years' time. There's also the question that that can only play for a certain amount of time. This is few hours of application. Batteries can't store energy over seasons. So in the UK we consume a lot more energy in the winter than we consume in the summer, and lithium-ion battery is not set for that. So those are technologies that we still need to develop and scale up. There's a question here.
I'm Bill Stetson. I'm a non-resident senior fellow here. I'm a trustee at the Smith Richardson Foundation. And in the 90s, I was a consultant to General Motors for new automotive, all their ideas. And there were many ideas. We rented half of Central Park one day and drove all these cars around. And I don't know what it amounted to, but it was a fun day. So I love analyzing what car companies are promising and what actually results. Now, the Volkswagen Group is in some trouble, and they're trying to dig out through a variety of EV technology. They're promising 24 new models throughout the three companies, from VW to Porsche, and with tremendous supercharging ability, tremendous range. And I'm just wondering, what do you think is going to happen in the real world? I have a Tesla now, and believe me, at 10 degrees in northern New England, there is no range. So
I'll let Venkat take this, but I'm going to say that, Venkat, one of the things that the question you've raised is essentially every new electric car that's coming online. Venkat does this analysis of what a battery can do for the car, and then he sends that analysis to me. And then I write a story about it, and I've categorized those stories as battery police. So he sort of takes the battery and figures out whether they can do all the large claims that people are throwing.
Yeah, so I think it's a very important question of what is possible. And you bring up two important effects. One is cold weather and fast charging. I think fast charging is gotten to the point now where I think it's pretty credible if anyone says you can charge 0 to 80% in 15 minutes. It is more than may not be there immediately, but it will get there. I think if someone says 0 to 80% in about 15 to 20 minutes, I think we will get there. The cold weather is getting a lot better. One of the beautiful things about batteries is that they're inefficient, but then that means that when it's cold, it heats up automatically. So one of the things that happens actually when it is minus 20 outside, like it is in Pittsburgh frequently, and I also drive a Model S, the range is half. And they've been getting better and better at managing the thermals. It's all about making sure the battery heats up to where it wants to be, just like humans, right? It wants to be in this beautiful air-conditioned 25 degrees Celsius environment. When it puts out peak power, it doesn't have any sort of perturbation. So the higher it goes, then cycle life fade happens. So people are figuring out thermal management issues. So I would say with high confidence that in the next 2 years, you can easily buy cars that have well over 300-mile range, probably at a price point somewhere between 30 and 40K, with a charging time of 15 minutes for passenger sedans. Okay. But that doesn't mean anything in North America, because 70% of the market is SUVs and pickup trucks. Okay, so which means that that's only a small sliver of the market. And so for pickup trucks, roughly a pickup truck is twice as inefficient as a sedan. What that means is that now double the battery pack cost. So the average price point that you can enter with a pickup truck today is somewhere around 50 to 60K. That would be somewhat competitive with the Ford F-150, which of course still holds the title of the best-selling car in North America. And so I think it's I think sedan is a solved problem, which is why I don't do any research on sedans. Sedans is done. And the hard part is pickup trucks and then long haul trucking. I think that's an extraordinarily hard problem. There it's a fundamental value proposition, because any weight you have in the battery pack is weight you can't carry as payload, and the value proposition is how much weight you move from point A to point B. So trucks is very, very hard. Last really hard problem is planes. But in terms of automotives, I think many of these things. I think from the 1996 GM days, I think we've come a very long way. I think at this point, quite easy.
There are lots of questions. So there are a few at the back. Okay, I'm going to take that one, and then there's a question here on this side. I'll take yours.
Good afternoon. Doug McClellan, McTriton Engineering. There's also been a wild card factor in the lithium problem. We know that it's hard to get the volumes out, get the production up, and whatnot. And slow and behold, I've watched this grow slowly more and more, and that is the factor of the supercapacitor, supercap. When this thing starts augmenting the lithium battery packs, it cuts the weight down radically, as well as augment and becomes powerful. As an engineer, we used to laugh at this thing, we said, you can't do this. When I started seeing vehicles driving down the street with no batteries, I said, wait a minute. So what do you see this as the impact in the foreign supply and manufacturing of these lithium batteries?
Sorry, I'm not sure. The question was about supercapacitors or about lithium-ion batteries?
Yeah.
It's about supercapacitors and their effect in being augmentation onto the lithium batteries, because that's where they're often do. What they're doing is they're putting them in parallel.
Yeah.
And it smooths out. Think of it like a battery multiplier.
Yeah.
It multiplies the effect of the lithium. For when it needs a surge of energy, it can do it without tearing into the battery, and therefore you can cut down the number of batteries and weight in the vehicle.
You should explain
explain
capacitors
yeah,
before we
so let me just
proceed.
quickly explain capacitors and batteries. Batteries are a form of chemical energy storage, so you move chemicals. The beauty about supercapacitors is completely electrical, so you just move charge. And everything is stored in the electrostatic energy. And so as you rightly point out, that means that they can last essentially forever compared to batteries.
Capacitors are right now in your phones. Like they are there in every piece of electronics you can see, even more so than batteries, but they are used for very specific applications.
Yeah, so those are capacitors. I think the things that you mentioned are supercapacitors, which are basically a subclass of materials. There's going to be definitely an important role for supercapacitors to play. The thing that they're very good at is delivering a lot of power. They're not as very good at delivering a lot of energy. So they're very voluminous and heavy for delivering energy. So you would not use them as the primary energy source, but you could use them as a way to augment this. This will be extremely important actually in markets where you need high power. So things like power tools and things like that where you need very high power. There's a very important role for supercapacitors to play. One that's my personal favorite is flying cars. There it actually is extraordinarily important because for takeoff you need a very high amount of power. So there are markets where this will become very important, and it's about managing the engineering of when you use the supercapacitor and the battery, which we're getting better at. So it's important.
There's a question back there.
Hi, Elena McGovern, AT Kearney. My question is about cobalt again. You mentioned it a little bit in the beginning and some of the supply chain issues. There's growing attention to some of the political and ethical issues around these supply chains. And a couple interesting data points recently. The London Metals Exchange said that it was going to start delisting companies in 2022 that don't follow clean and ethical standards. That's, that has the DRC cobalt mines, right in their target. BMW has said it's intentionally going to be starting to source EVs, from other countries to not deal with child labor. And I think it was just 2 weeks ago that Tesla, in a closed-door meeting, someone said that Tesla expects there to be a tech metal supply shortage in the next couple years. I mean, it was very soon. So I just want to get your views on, what is the outlook for the cobalt market, new sources of supply, how you said prices even doubled from last year to this year. What are we looking at, and especially as some of these political risks and companies are increasingly having to demonstrate that they have what we call, clean supply chains?
I'll let Mitali take that answer, but I'll give a historical point here, which has been one that lots of academics have made to me every time I've asked this question, which is there has been no material that we've really ever run out of. And that's because economics of elements are such that when you start hitting constraints of cost constraints, essentially, we move to something else that works. And so, sure, cobalt is the super cop here, and we might find a cobalt alternative at some point. But that is the historical point. We've never run out of something that we really need for whatever our application demand has been.
And just to kind of go back to the point that I was mentioning earlier, like last year we saw prices of cobalt more than double, but this year actually prices have stayed flat. Prices have actually come down and they have stayed flat early this year. We haven't seen any increase in cobalt prices up until now. They might start increasing again, but and that's the way the industry is kind of working towards it, right? As I mentioned earlier on, like industry is also already looking at making sure that we are either having low cobalt cathodes or even working towards no cobalt in cathodes. So there are also some, technical advancements happening around where we can ensure that these batteries completely eliminate cobalt. One of the examples around that is vendors kind of looking at lithium sulfur batteries. Again, a technology which is still several years out, but there are, investments going on around that. Another kind of battery type that several vendors are also looking at are solid state batteries, which is a kind of battery where your electrolyte would be electrolytes usually are in liquid state right now, but you will actually have a more solid state electrolyte, which will actually increase energy density of your battery. So those are also, currently under innovation, and vendors are trying to develop that. But at least in our forecast at WoodMac, we don't expect to hit a cobalt supply constraint anytime soon. We think that we have enough supply to, meet the demand at least for the next 5 to 7 years.
Just to calibrate, the cobalt amounts are dropping drastically, right? So now it's about down to 5 kilograms per car, and it will probably get to sub 2-3 kilograms per car. So I think it's dropping dramatically.
Right. The other thing to keep in mind is lead acid batteries are in at least the rich countries mostly recycled, and lead is a good material to recycle, so there's reason for that. But we've become really good at recycling lead because it's cheaper to use recycled lead than mined lead. That's going to start happening in the cobalt, in just lithium-ion industry in general, but specifically looking at cobalt. So Audi last year worked with Umicore, which is a metals company, to develop a technology to have essentially 95% of battery materials, valuable materials, recycled. And we're starting to see that play out on large scales in China, where now electric cars in the thousands have been around for 10 years, and that's about the life of a lithium-ion battery if it were just sitting around. And so recycling is starting to take off. So that's the other way in which we can overcome material constraints.
The other thing that I'll add is also kind of banking onto what you said is, for energy storage applications, we're also hearing bringing back EV batteries for second life applications in energy storage industry. So that's another thing that is being explored by grid storage vendors, where they can actually bring back used EV batteries for grid storage applications, just repurpose them, because EV batteries still have a decent amount of cycle life left, so they can actually be deployed for energy storage applications. We just need to repurpose them. So that is also going to impact the demand of these batteries in the future and bring down pricing in the future, and overall impact, the raw materials that we need.
There were a few questions that have been raised hands over there that have not gotten to. So I'll get to one over there, and then I'll come back one here. So that one. Yep.
Some years ago when electric cars were still ramping up, there was a lot of talk about having networks of charging stations. And I was thinking that with the issue of recharging speed and the increased danger that goes with that, has anyone looked at the idea of just taking the battery out rather than recharging the battery in the car?
Yeah, that's a good question. And the battery swapping technology, what you're referring to is battery swapping technology. Lots of people have tried it. Well, the famous examples is, Tesla developed the ability to try and swap out batteries in the Model S, then did not go down that route and abandoned it. There was a spectacular failure of a startup called Better Place, which was an Israeli startup that got to $1 billion valuation at some point and then failed to take off. And it's an economics question, because
it's a very simple calculation. Each battery pack is now not, you have to own more than one battery pack for you to basically be able to go, right? Because so essentially now the cost now becomes 1.5 times the battery pack cost, and battery pack is still 50% of the vehicle cost, or 40 to 50% of the vehicle cost. So it basically bumps up the cost far too much. However, in markets where this is not the case, for example, in two-wheelers and three-wheelers, there's actually a real important play for battery swapping, where you need to be on the move all the time. So there's an important place there, but I think it's very unlikely that this will happen in automotive, but it will happen in trucking, where trucking is basically fleet-owned, so there's a fleet angle to it. So if you have a fleet of vehicles, then it actually makes economic sense to do swapping. So fleets and two-wheelers we'll see swapping. Every other market, no swapping.
And swapping is currently in use in India in two-wheelers and three-wheelers. So three-wheelers are famous in India and Southeast Asia, and they are actually using those technologies right now. So battery swapping stations are being built in Mumbai and Delhi. China is still trying automotive. So there are two car companies in China, NIO and BJEV, who are building out their own battery swapping stations. So the technology, most technologies don't die. There might be some use case applications, but yeah, Venkat's right. It doesn't seem like it's going to be a mass market.
But this is the one thing in the battery business. It's almost like a religion. There are those that believe in swapping and those that don't, and it's impossible to convince one side or another side.
All right, there are questions here. There's one in the back that's been raised, so I'll take that one and take yours and then yours.
Yeah, thank you for your insights. My name is Ravi Deepak with Science and Technology Corporation, and when you look into like the history of lithium ion, it seemed like when I digested the market, it was like laptops, cell phones, and Tesla sort of led to like the institutional investment into this technology. But when's the phase shift to like hydrogen or other like battery storage technologies? And especially when you look at emerging markets where institutional investments haven't been made, such as India or other places, do you think these technologies can take strongholds?
Yeah, I would just correct that by saying it's laptops, smartphones, and then electric cars, not Tesla. That's a Western viewpoint that we need to correct, because honestly, the place where electric cars are taking off is China. Not, Tesla is the one that we know here because it's in our faces, and we have a CEO who is in our faces all the time, but the real players are in China. So yeah, I think that's a good question.
So hydrogen has actually, I would say hydrogen had just as much or even more investment than batteries over the last 30 years, and we've
but research, not in the startup space.
Well, for good reason. So hydrogen fuel cells. Japan is one country that has pushed it enormously. Honda and Toyota have invested an enormous amount of money in building fuel cells for automotive and stationary power. The challenge with hydrogen is every part about it is problematic. Making hydrogen is hard, storing hydrogen is hard, using hydrogen is hard. So we still haven't figured out efficient ways to store it. You don't want to store it in as compressed hydrogen. So there are safety challenges associated with that, but there are some solid state materials. People have spent a lot of time trying to make that work. It has still not come to the state where it's anywhere near prime time to compete with lithium ion for automotive. I think that ship has sailed. Maybe it might be possible to do to make a dent in trucking and aviation. I think their weight is actually super important. Their hydrogen can play a very important role. But I think for cars, it's probably the ship has sailed.
And the smirk that you saw on his face a little bit was because he used to be a fuel cell researcher before, and he's a convert. So when he's saying that, I think you should believe why the future for automotive applications is batteries. And you can nerd out about him, why so many battery researchers are fuel cell researchers, and vice versa at some point. There was a question here which has been there for a while. So the lady in the fourth row, and then.
Is this on? Yeah. Hi, my name is Kay Kaufman. I'm with Fluence Energy, where in fact we are thinking about what happens to the, storage when markets change and things like frequency response markets bottom out. We are thinking about it very hard, as a matter of fact. And so the move towards long duration batteries, particularly, is also provides a lot of flexibility. And obviously, there are issues of contracting. We know the market is going to change, and storage companies are going to have to be flexible when, a market that they have a customer in changes, and they've got to figure out a way to keep the value of that storage. One issue there is being, with value stacking, is being able to monetize all those different streams, which is a regulatory issue, which we're certainly seeing in the United States and I think in Europe. I don't know if you can talk about that.
Yeah, I mean, as I mentioned, we are definitely not there yet where we are not seeing value stacking happening. And I think more so when you think about pairing your storage with solar, where you can actually tap into a lot of revenue streams. That's definitely one of the challenges that we are seeing in the industry. But I think the way the market is looking at it is trying to overcome some of these issues as an industry together, where we can get to some of those results. The other way the market is also looking at tapping into different value streams is through the software layer. So a lot of advancements are happening where, you know, a lot of software vendors are trying to guarantee you where you can get into, you know, getting a lot more revenue streams and getting a lot more value out of your storage system. So that's also another thing that's happening in the market. But yeah, I mean, for the time being, it's definitely one of the challenges that we keep hearing a lot about, where the industry knows that you know, we have all these revenue streams, but it's hard to tap into them.
There's a question there.
Hi, I'm Julie. I have just a question regarding to what was earlier discussed during this panel. So you discussed that batteries, the production of batteries should be located around the world and not be like monopolized at the moment in Asia. So I was just wondering, if that would be the case, would you expect that car manufacturers, and mostly European car manufacturers, would then take the battery production in-house? Because that for them would be a lot more expensive. So how would they then be able to sell their electric vehicles to consumers that already don't really want to pay the price for the electric vehicle? Thank you.
I can take that. So one of the things with batteries and just car companies in general is that there are good reasons why startups like Tesla, despite all the difficulties, and startups even in China, are doing better than the traditional car company. That's because they are two different types of technologies altogether. You use electric motors to run electric cars. You don't need as many parts in an electric car as you need in an internal combustion engine car. And so something that the large car companies have tried to do is use the same platform that they were using for their old cars to then make electric cars, and that's leading to inefficiencies and poor performance. Whereas when you come to it as a fresh start, Tesla is an example, Rivian is the other example here in the US, they're able to produce cars that are just better. And this is proven out over the last year. So Venkat did analysis with the two big electric cars that have come out, Jaguar I-Pace and Audi e-tron, both from car companies that are loved otherwise, and they've proven not to be able to do everything that an electric car can do.
That is largely due to the point that you just made. So let me just maybe 30 seconds explain what it means to make a battery pack. So there are three aspects to it. You take a cell, and then you make it into a module, and then you could take the modules and make it into a pack. And so pretty much everyone buys cells from someone else, or buys modules from someone else, or buys packs from someone else. So it's a question of what you buy. And what you buy gives you more engineering tunability. And so Tesla, on the other hand, buys their cells from Panasonic, and then makes the modules, makes the pack. And that means that they understand everything from the module level. Other people may buy modules, in which case they have only control from the module level, which means that you can't engineer it to the point where you use all of the pack that is available. One of the interesting things we found out in the analysis that we did on the Jaguar versus especially the Audi case, Audi and Jaguar both versus the Tesla case, was they're leaving essentially 10% on the table. The energy is there in the battery pack, but they're not using it because they're afraid that it will not last the cycle life that they're guaranteeing you. And so many of these things stem from the fact that someone else is making some part of your value chain. I think it's going to be extraordinarily hard for all the automakers to turn into battery cell manufacturers. I think it is very, very unlikely. They will continue to buy cells from others. But I think bringing more of the module engineering in-house will be extremely important. Maybe bringing some cell engineering in-house, but not making them themselves. I think that's probably the most likely scenario.
That said, people are going to try. So Volkswagen has just announced this week that they are going to try and make their own batteries. And so we'll see how it shakes out, but I think it's right on that. The question here.
How are flow batteries looking for the electric grid?
It took a while to come to flow batteries. This is clearly not an audience that loves batteries so much that flow batteries is not come. I can answer, but do you have thoughts?
Yeah, from an energy storage industry perspective, this is something that I always say. Flow batteries will start to make sense for niche applications. So as the market is looking at long duration systems, as was mentioned earlier, we are thinking about seasonal storage. We are thinking about systems that are more than 10-hour duration systems. We want to cycle them more and more. We're looking at longer life, bigger projects. That's where we think that flow batteries are going to outperform lithium-ion batteries, because lithium-ion batteries, the economics starts failing when you're looking at systems that are more than 6-hour duration. That's when your lithium-ion batteries don't perform really well.
Yeah, and it'd be fun to explain what flow batteries are because of the fact that they can. So flow batteries are really fun to think about because they are batteries that are unlike a battery that you know. So batteries are just these boxes of black plastic, usually outside, and metals inside. Flow batteries have tanks with liquids in it and pumps. And what you essentially do is your energy is stored in these liquids, and then you use a smaller space to be able to convert that energy into electricity when you want it. And so you could keep increasing the size of the tank and the pumps, and you can store more and more energy without having to multiply the amount of technical battery electrodes that you need. And that's why you're able to get what you get scale. So you're able to store maybe 6 hours worth of energy at the same cost in theory as a lithium-ion battery would be able to do it for an hour. But none of that has shaken out yet.
A flow battery really is a fuel cell, but it was not attractive to call them fuel cells because DOE would not give us money if we called them fuel cells, so we call them flow batteries. But really, it's the exact same as a fuel cell. You have a fuel and then you're flowing that through.
Yeah.
So.
Yeah. I'll take that question, and I'm going to come to future applications because I know there are some that
I don't know if this has been covered earlier, but Doug again. One promising technology is one of the things in batteries is what we call the positive electrode, and it destroys fast. But in the case of iron batteries, it's been slow to develop and slow to get into yield of good production cost. However, one of their assets, do you see this increasing and getting better because they have tremendous longevity? I mean, in the Ford Museum up in Detroit every year, just for fun, they recharge the iron batteries in Thomas Edison's electric vehicle and drive it around the parking lot again. They've been doing this for 60 years. Do you see any increase in the volume in iron battery technology?
I don't know what this iron battery technology is, and I think I've looked at pretty much every chemistry, so I'm not sure what this is.
Not 100% sure.
Yeah.
I should.
We can look at it later at some point.
That's a good first class in my battery scores.
Yeah. There's a question here, and then I'm going to come to flying cars. Because Venkat told me they're going to become a reality. I don't believe him, but we shall get to it. There's a question there.
Thanks. Sonia Tigges with the Institute for Advanced Sustainability Studies. I was wondering if you could go just a little bit more into the recycling issue, because as cars are sort of traded internationally, I'm wondering if this is sort of increasingly going to become a problem, if a battery is produced in one country and then sort of disassembled later on in another. Are there already any norms, like international standards, or is this something we're going to have to be looking into more in the future? Thank you.
Maybe I'll offer some thoughts on recycling, and then you can talk about the regulatory aspect. So the volumes have not been there yet for people to really think about recycling, but it's actually pretty easy to recycle. It's a little like bringing, it's like pumping some juice back into the battery. So all you need to do is refresh the electrolyte. That brings you back 90% of where you were. So if you have an EV battery that is degrading, and you put some fresh electrolyte, that brings you maybe 80 to 90%. There's now very good ideas around recycling cobalt from the battery. The only thing you would recycle is cobalt. Everything else is not economically viable to recycle. There are now ideas where you could take the one of the things that happens as the cells age is the size of the particle that is there in the cathode increases. The size of the particle increases, it cannot deliver as much power. So all you have to do is do another processing step where you would then bring back the size to the optimal size you would want it to. So there are hydrothermal, other treatment technologies with which you can refresh back the cathode itself. So I think it's very likely, I mean, given what we've learned from lead acid, and recycling lead acid is a much harder problem than recycling lithium ion. So I think it's just that there's not volume, there was not resources. There's actually now a massive investment from DOE. They've now set up a facility in Argonne to do detailed research into recycling. I think it's actually not it's not nearly as hard a problem as trying to find like low cobalt alternatives. So I'm very optimistic that we will be easily able to recycle.
Yeah, and on the regulations, I think you're right. Lead acid is harder to recycle, but because of regulations, we've also made it possible for the lead acid industry to get into recycling. One of the things that I was surprised by in the last 6 months is that Europe put out sort of a draft looking at how to encourage lithium-ion battery recycling. And in that draft, they say the kinds of regulations we are looking at, I'm rephrasing this, are what are already in place in China. So this is another weird case where we are learning about regulations of an environmentally friendly way of using technology from China these days. And so I think you're absolutely right that without regulations, we're not going to be able to touch upon recycling. Okay, flying cars. The last I talked to experts, apart from you, about flying cars was they were considered magical. Tell me why they're not going to be anymore.
So unlike Akshat, I don't write that many popular pieces, but I did write one popular piece in Conversation where we built an applet where you could put your own next generation futuristic battery chemistry, and we'll tell you how long a realistic flying car would go. I think so 2017 was when I made a massive shift in my research priorities and transitioned completely to flying cars, planes, and trucks, and because all of the markets seemed easy from a battery perspective. The hard part about flying cars is takeoff and landing, especially for these eVTOLs. Not planes. Planes actually landing is easy, but for eVTOLs, flying car type, I don't know if flying cars is a funny term, but basically what happens is in takeoff, they are in sort of a helicopter mode. So they're basically pushing the air up or down, depending on whether you're going up or down. And then they tilt, and then they go like a normal plane. So that's how most designs of a flying car works. And so the hard part is when you take off and land, you need to push an enormous amount of air. And so you have a power requirement that is very, very high compared to the energy required during cruise. And so the challenge is how do you make batteries that are fast discharge capable? And this is a market that nobody cares about in the automotive, even Tesla, right? This is like asking being on ludicrous mode for like a minute, right? So ludicrous mode, for those of you that don't know, is 0 to 60 in 2 seconds or so. So you need to be in this same power delivery mode for about a few minutes if you have to take off, and actually more importantly, a few minutes when you have to land. And it's because the landing and takeoff are essentially similar, because for landing you have to push all the air out to land. And so it's essentially the same power requirement. It's actually, as you know from your laptops, by the time it gets to 10%, you can't play your YouTube videos and so on, because delivering high power at low state of charge when the battery is nearly depleted is very hard. So that's the hard part. So these are the two things that need to happen. So we need to be able to deliver fast discharge, and also be able to deliver that at low state of charge. So this is the hard part. But in terms of technology, with sort of near-term technology, we can build flying cars, and we have ongoing projects with Airbus, several other eVTOL companies, and I think there's a straightforward way to get to things that can go about 40 to 50 mile range. And what Uber is thinking is you need to get about 100, because you would want to do at least 5 trips, 20 miles. And at that point, it would be reasonable, because you can imagine after 5 trips you would recharge and so on. So I think, I've stuck my neck out in my in my essay for TR35, I said by 2025, I would have personally flown in a flying car for a meaningful trip, not a toy trip. I mean, like, so maybe like from Carnegie Mellon to Pittsburgh Airport, which is like 25 miles. So something like that, I think, is in the near future. We don't need like 10 breakthroughs to get there. I think we will get there. So what about planes?
Exactly. What about planes?
Planes are really, really hard. So regional planes are doable. So things like a Pittsburgh to DC is maybe doable. The real planes is just very, very hard. Anything beyond an Airbus A320, now we can't say Boeing 737, but Airbus, beyond that sort of size, it's impossible. Probably things will go hybrid electric. Even if you go hybrid electric, I think you get a lot of the emission benefit. But jet engines are pretty efficient. They're an amazing engineering feat, and the safety of batteries is not at the point where I think one could reliably use that. So I think a lot about planes. I work with a company that is trying to make hybrid electric planes for regional transport. I think regional is doable. 300 to 500 nautical miles. 10 to you have to do miles and passengers because it's a trade-off. And so I think you can do about 20 to 50 passengers sub 300 miles or tens of passengers for about 500 miles. That's the limit of this is the limit of what we know is possible with any chemistry. Right? I'm not constraining myself with what is possible today. This is with any chemistry in the known periodic table, unless we invent a new particle with which we shuttle between the anode and the cathode, so maybe an electron or maybe some other particle. But if we still use any ion, and it doesn't need to be lithium ion, it can be sodium ion, any ion, hydrogen, proton, any of these things, this is basically the fundamental limit of what's possible. So planes are very, very hard.
Yeah. And with that, I think our time is going to come to a close. If you take something from this, I would say the battery hype is real, but to have that reality play out, you need to understand the details, and you should not shy away from the details. Thank you so much for coming here. Thank you, Venkat and Mithali and David and the Atlantic Council for hosting this.